So I finally had the chance to get some work done on the motor controller for my Gingery style lathe. And I'm going to take the time in this video to kind of show you how it works and just give you a demo. Unlike the traditional Gingery lathe that uses a quarter to a half horsepower motor and belt changes with various pulleys and a counter shaft to get the different RPMs, I'm just using a DC Treadmill motor, pulse width modulating it with some software control in order to get variable speed, and it also adjusts based on load to maintain RPM. So I'm going to show you basically what I've done. Here's my control box, which basically has the brains of it. I'm using a PIC 18LF14K50 right now, and that seems to work out pretty good. Here's the inside here. I have all the higher voltage stuff, the high power MOSFET, flyback diode, all that stuff that is used to control the motor. You can see it's rated at 2.6 horsepower at 30 volts DC. I'm pulsing it at around 150 to 160 volts DC, so I don't really get up to 100% duty cycle. I've only needed to get up to maybe 50% to get 2,500 RPM, but it works pretty good. At some point, if I want to get more torque at lower RPMs, I might add an additional, additional shaft and pulley setup to get maybe another ratio out of that. But it works pretty good. And I have an Encoder Wheel. Basically a optical detector, emitter detector pair there. I'm using a QRD 1114 for that. Initially I had it mounted on the inside, but these are just, they're not ball bearings, so I put the oil in there and the oil kind of splatters everywhere. And here's my initial Encoder Wheel, and it was starting to get really dirty, and I think that was maybe affecting the readings, so I built this out to keep it kind of on the outside. Once I have the final housing and all that stuff done, I'll figure out a permanent mounting solution and try and isolate that, from any oil or debris that might get on it to keep the readings good. But overall, it works pretty well, and I'll go into some, separate clips. So here's the control box for the lathe motor controller. I don't know if you can see the display. It's a little bright. I don't know if it's going to show up on the camera, but hopefully it does. Anyways, there's a couple little safety features built in. If the knob's not zeroed out, which this controls the RPM, if it's not zeroed out, you have to zero it first when you first start the machine. And you have to hold the menu button down before you can enter an RPM. Basic operation, you just set the RPM. The bottom number is the target, the top number is the reading. And that's basically it. There's sub-menus. Press the menu button, and these are just, information for me to determine how the machine's working. If you hold the menu button down, there's a little indicator, that pound M, and then if you press left or right, you can change to other menus. The system uses a PID Control Algorithm, proportional integral derivative, and here you can set the constants for that. Basically, so that's that. Right, and then the next menu, basically some maximum is minimum. Maximum adjust is just the maximum adjustment that can be made each cycle on the duty cycle value. Here's the maximum duty. The absolute maximum is 1020, so I kind of have it a little bit below half. If I put 300 for a duty cycle value, I'm going to get about 2,500 RPM out of it right now, so 400s works pretty good as a maximum right now. Minimum RPM, maximum RPM, encoder slots, that's just the number of transitions on my encoder wheel. Then we can go back to the main one. Alright, there's a hole over here. I had the reverse switch initially there, but I moved it to the back of the power supply. I don't think I'm going to be switching it too much. You can see it working. Zero the speed, flip the switch. Goes in the other direction. Zero the speed, flip the switch. Goes back in the normal direction. Another safety means when I have the case, I have one of these push twist emergency stop switches, so you can see it working here. Stop. And then to turn it back on, you have to, well, not to turn it back on, but to get it going again, you have to twist it. And then, as you can see, it's back to the 0 knob hold menu before you can turn the machine back on again. Basically, there's a little algorithm in there that detects when the motor's stalled, and if it is, it just goes back to a state that it's in when it first, when the controller first turns on. Inside this box, I have basically the power supply is the MOSFET that's driving the motor, flyback diode, and other electronics that are needed to make this work. Fan, this is really just a, ATX power supply case. I gutted it, used the fan, put the fan on the outside so I have more space on the inside. It works actually pretty good for a project enclosure. So if you can find these, I got this one for like $5 from, like a recycle store or whatever. And so that worked out really well. So I'm going to show you just a demo of how the machine operates. I'll get it up to maybe, I could do 2,500 RPM just so you can get an idea. The camera will probably start shaking. I'll show you how, if you load down the shaft, how it compensates for that and tries to maintain RPM. I'll get it down to 60. 60 is a little questionable. It does pretty good, but you kind of have to ease into it. So if I was bringing like a cutting bit into it, I wouldn't jam it in there. I'd kind of ease it into it. But it works pretty well. As you can see, it's maintaining. It's maintaining the RPM, at least on the display. It looks like it is to me. Then we can go up to like, 150, kind of like there. It compensates. Really. Compensates. Then we can go up to 500. That. Compensates. Some things I might have to work on further if I need to. Is the frequency response and how it's doing, but it seems to work out pretty well. RPM. Now the camera might be shaking just because I don't really have this on a very stable table, but works pretty good. Get it up to 2,500 and you can kind of get an idea. What it's like at 2,500. I'm not going to hold the shaft at 2,500 RPM, but I wouldn't necessarily recommend doing it. I have a welding glove. It keeps my hand fairly safe. Obviously, you don't want to be grabbing the stuff, but seems to work out okay. So I'm going to set it to 150, and then I got these like carbide tool bits, and I didn't realize that I had to dress them up, before using them, so they're pretty dull. And the tool bit isn't actually aligned center to the shaft, but this is just, I got my safety glasses on, just in case, whatever. But I'll bring the dull bit into the shaft and you can see kind of how it compensates. In like a real life case. So there's that. And that's at 150. I can go down to, say, for giggles, I can do like 40 RPM. And, I don't really expect too much from this. And as you can see, the rotation's a little choppy, but still compensates for it. Even though it's like, really choppy. So if I wanted to go down to, 40 RPM or 10 RPM or something, I'd have to do something with the, the pulleys and try and get more torque out of it that way, just to get those lower speeds and have it be a little bit more consistent. Or maybe I could work on the algorithm a little bit more, but at this point, I don't think I'll be operating it at those speeds anyway. So this is 60, and that works pretty good. But like I said, I have to ease it in with 60. If I start jamming in there, it'll get a little choppy. But it still works okay. Probably be a little bit better with a sharp tool bit. And then we can go up to, 500. You can see how that goes. But I do like the treadmill motor works pretty well. It's got a lot of horsepower, so let me get a really good job. And as you can see, no noticeable change in speed or anything on that. So that's that. Yeah. And then next I'll do the headstock and cast the headstock, which is over here. I'll cast that, and I'll bore out the hole with this setup, and I'll be moving.